For the last 70 years or so, every single computer has followed one simple rule: be perfect. One wrong bit, one tiny error, and the whole thing comes crashing down. But what if we built a computer on a foundation of, well, imperfection? What if we took an AI with all of its creativity and all of its flaws and asked it to be the brain of a machine? Well, today we're doing something kind of wild. We're not just talking to an AI, we're going to turn it into a CPU. So let's look at this tale of two processors. On the left, you've got a classic, the 6502. Just think of it like a light switch. It's either on or it's off, a 1 or a 0. It's built on the hard, cold laws of physics, and if a single one of those bits flips unexpectedly, the whole system can just die. Now on the right, we have Llama 3. This isn't a light switch, it's more like a cloud of possibilities. It runs on probability, and those things we call hallucinations, they're just a natural part of its world. So you've got this fundamental clash, right? A rock-solid calculation versus a creative guess. And that brings us to the crazy idea at the heart of all this. We are going to take this creative, sometimes unpredictable AI and give it one of the most rigid, unforgiving jobs imaginable: running a computer's core. We're not just building another program here. We're building a self-healing neural kernel, a system that can actually find and fix its own mistakes completely on the fly. Okay, so how in the world do we pull this off? Well, to make this work, we have to translate the language of computers, silicon, into the language of AI. We have to take all these concepts that we know, like memory and processing, and find their equivalents inside the world of a large language model. So how do we get a stream of words to act like a chip made of silicon? Think about literally any device you own. Your phone, your laptop, even your smartwatch. They all run on the exact same basic principle: the von Neumann cycle. It's really just a three-step dance. Fetch an instruction, decode what that instruction means, and then execute it. Fetch, decode, execute, over and over again, billions of times a second. And this is where it gets really, really interesting. On this slide, you can see how we're actually mapping those classic computer parts to our new AI-powered CPU. The program counter, which keeps track of where the computer is in a program, for us, that's just the cursor in our text. The accumulator, the little workspace where a computer does its math, that's the AI's internal thought process, its hidden state. And the computer's RAM, well, that's the AI's context window, our limited, precious, and very expensive memory. Here's probably the biggest difference between the two. A regular CPU, it thinks in black and white. It is all about ones and zeros, on or off. But an LLM? Nah, it thinks in all these shades of gray. It's not about absolute rules. It's about probabilities and patterns that it's learned over time. It's this dense cloud of correlations, which is fantastic for handling messy real-world problems, but it also means we can never be 100% sure it's right. Okay, enough with the theory. Let's actually see this thing in action. We're about to do something that honestly feels like it's straight out of science fiction. We're going to give our neural CPU a piece of broken code and just watch it heal itself. We've got a fancy term for this: self-healing semantic assembly. It sounds a little complicated, but let's break it down real quick. Self-healing is obvious, it fixes itself. Semantic is the key part. It understands the meaning of the code, not just the punctuation and syntax. And assembly, because it's building a correct program from a broken one. See, it's not just running code, it's thinking about it. So the mission is pretty straightforward, right? Our neural CPU is going to look at the broken code and the error message it spits out. Then it's going to figure out what went wrong on a conceptual level, not just where the typo is. After that, it'll rewrite the code to fix the problem and then try again. And it's just going to keep doing this over and over until the code finally runs perfectly. All right, here we go. We're firing it up. The kernel tries to run the code and bam, it crashes. We get a standard Python type error. Now, for a normal computer, that's it. Game over. But for our neural CPU, this isn't an error. It's a clue. So the kernel takes a look at that error, suggests a fix, and tries to run it again. And it fails again. Now, this right here, this is a key moment, because this isn't a one-and-done attempt. It's a learning process. See, for this system, failure isn't a bug. It's a feature. The system doesn't get discouraged. It just gets more information for the next try. And here it is. This is where the magic happens. On the very next attempt, the LLM has more information to work with. It looks at the error and has this moment of insight. You can literally see its thought process. The error is a type error. Radius squared is a string. It gets it. It understands the concept behind the error. It rewrites the code correctly, and this time, it works. The system has healed itself. Now, you might be thinking, okay, that's a cool party trick, but this is so much more than that. What we've just witnessed is basically the hello world moment for a whole new era of computing. We've just seen the first little flicker of life in what could one day become a full-blown AI operating system. So, what is an AI OS, really? Well, imagine an operating system that doesn't just run programs, it actually thinks. The kernel itself is an active agent. It can monitor its own performance, schedule its own thoughts, and even boss around other AIs, like they're just apps on your phone. This is a massive paradigm shift in how we think about operating systems. A traditional OS, like Windows or Linux, is kind of like a meticulous librarian for your computer's hardware. It just manages memory, storage, and processing time. But an AIOS kernel, that's more like a CEO. It's not managing hardware, it's managing ideas, goals, and the most valuable resource in the entire AI world, that precious context window. Okay, so let's cut to the chase. Why does any of this matter? Why should you care about building a CPU out of an AI? What does this actually mean for the future of technology? Well, it matters because it's time for us to grow up a little bit. For the last few years, a lot of what we've been doing with AI is, well, you could call it vibe coding, right? You just kind of poke the model with different prompts until you get a result that feels right. This new approach, context engineering, it's about being deliberate. It's about designing and building these AI systems with the same rigor we used to build bridges and skyscrapers. Look, the future here isn't about AI or traditional computers. It's about AI and traditional computers working together. In this kind of hybrid model, we use the AI for what it does best, understanding our messy, often ambiguous human intentions. That's the decode step. But when it's time to actually get the job done, the AI writes classic, old-school code and just hands it off to a regular computer for a perfect, predictable result. You get the best of both worlds. But let's be super clear about something. We are not about to throw away our current processors, not by a long shot. A modern CPU is an absolute speed demon, executing billions of instructions every second. Our neural CPU, it's more of a deep thinker, processing maybe a few dozen words per second. The goal here isn't speed. It's about creating a totally new kind of processor that runs on a new kind of code, pure, unadulterated human intent. And that, of course, brings us to the big, scary question at the end of all this. We're building systems that are incredibly powerful, but they're built on a foundation of uncertainty, of probability. So I'll leave you with this thought. Would you really trust an operating system that can think for itself, but might also just, hallucinate your most important files out of existence? The age of the reasoning processor has begun, and now we have to figure out how to live with it.